Welcome to Life with David. I'm David, and today I'm continuing my research into the programmable input-output features of the RP2040. Last time, I explored PIO forced and exec instructions while using C. This video generated several great comments and questions. I thought I would address those comments, so why don't you join me as I do a deeper dive into forced and exec instructions. My previous video covered forced and exec commands using C. A great question came from Michael Bryan, who asked if forced and exec instructions could also be used with MicroPython. I thought I had seen some reference to that capability, so I did some research. I'll cover my findings in just a moment. But first, I received a comment from Slim Hazard who suggested a much better way to address the offset for the different loops of the PIO program when using C. After some clarification, I was able to vastly improve the portability of the PIO program. I'd like to thank Slim Hazard very much for the assistance. Let's go through these improvements now. As a refresher, last time I separated the PIO program into 4 loops. I branched into each section from the C program by using the main PIO program offset added to the loop offset from the start of the PIO program. I hard-coded the loop offsets based on information I got from the PIO header file. I was able to demonstrate the forced jump, but any change to the PIO program would require changing the hard-coding of the loop offsets. Slim Hazard pointed out that I could use public labels inside the PIO program and simply call them out from the main C program. Brilliant! In our example, let's look at the start of the second loop where we blink LED 1. I'll add a label that starts with the word public where I want to enter the PIO program. The keyword public will automatically create a definition of the label that can be accessed by the main C program. The label offset name is comprised of the PIO program name followed by the word offset followed by the label name. This PIO program is named EP11 Demo, so the label for LED 1 entry would be EP11 Demo _ offset _ LED 1 _ entry. Where can I confirm that? You can find the public label names listed in the PIO header file. Here listed the 4 entry points for my PIO program. In the main C program, I used the PIO state machine exec command to transmit the jump instruction to the state machine instruction register, just like before. But this time, instead of hard-coding the offset, I'll use the loop offset label added to the PIO program offset. This allows us to modify the PIO program while maintaining the proper entry points. Pretty slick. Next, let's investigate what kind of forced and exec instruction capabilities the Pico has while using MicroPython. I found that most of the functionality of the C exec instructions exists in MicroPython with one important exception. Currently, MicroPython does not support immediate execution of the jump instruction. This makes it difficult to branch into different parts of the PIO program from the main program. However, there is a workaround. Let's compare the C program exec instructions with the MicroPython exec instructions. For instance, from the main C program, an immediate forced instruction is called by the PIO smExec function. In MicroPython, an immediate instruction is an instance of the state machine class that is defined by the PIO decorator. In this program, sm1 is the class specified by the decorator, and the sm1.exec packages the instruction for execution by the PIO. The instruction is contained within quotation marks and has the same format as the PIO MicroPython instructions. However, any variables are entered using a format similar to that of a print statement. Unfortunately, as I mentioned earlier, jump is not supported at this time. The workaround is to force the desired program counter into either the X or Y register and then move that value into the program counter. It works, but it does clear the value of the X or Y register, so you have to be careful in case you want to save something from that register as you change program locations. But where do we jump to? Well, in MicroPython, this is a bit more difficult than in C. As I mentioned in episode 10 of the PIO Chronicles, the start of the PIO program will have an offset from the start of the PIO instruction memory. In C, we get that offset by using the PIO add program function. That function does not exist in MicroPython. Here we have to read the instruction address register prior to starting the state machine. There's an instruction address register for each state machine located at offsets of D4, E6, 104, and 11C hex from the start of the PIO register base addresses. These registers are detailed in section 3.7 of the RP2040 datasheet. If the state machine has been configured but not started, then the instruction address will be at the top of the PIO program. This information, along with the loop offset to the start of each loop, can be used to generate the desired program counter value to be forced into the PIO. Unfortunately, MicroPython doesn't have public labels for the PIO program or even a header listing where you can verify the addresses of the instructions. You have to count the number of instructions and hard code the loop offset along with the PIO program offset. Let's mention the other two PIO exec instructions before I demonstrate the program. The MicroPython version for out exec32 is out open parentheses exec, 32 close parentheses. And the MicroPython version for move execx is move open parentheses exec, x close parentheses. These MicroPython commands work identically to their C counterparts. For comparison, I've converted the LED blinking program from C to MicroPython. This program has 4 loops that blink LEDs 0 through 3 with different patterns. As a reminder, the PIO and main MicroPython programs are contained in the same file. Please see episode 1 of the PIO Chronicles for more information. I've also included the C version of the PIO instructions in the comments for reference. I'll use Thani to display and execute the MicroPython program. First, we'll include various libraries to connect to the PIO, the GPIO, the state machine, time, hardware register access, and the PIO assembler. This is the function that returns the current state machine instruction address. This part calculates the address of the instruction address register for a given state machine, and this part reads the value. This will be used later to determine the start of the PIO program. Here is the PIO decorator where we set 4 GPIO pins as outputs and then define the PIO blink program as EP11 blink. The PIO program consists of 4 loops, all independent from each other. The MicroPython and C versions of the PIO program work identically. I've included the C public entry points in the comments for reference, but they're not functional in MicroPython. I'll quickly review the PIO program. For more information, please refer to episode 10 of the PIO Chronicles. Loops 0, 1, and 3 use the jump Y decrement to implement timing loops. Loops 0 and 1 are identical with the exception that they blink different LEDs. Loop 2 streams instructions that are sent to the transmit FIFO into the output shift register and then sent to the control logic using the out exec32 command. A blocking pull is used to allow the main MicroPython program to control the timing. Loop 3 grabs instructions from the transmit FIFO and stores it in the X register. Then at the appropriate time, the move execx command executes that command. In this case, the command tells the PIO program which LED to blink. After the PIO program, we'll configure the state machine. I'll call the configuration SM1 and will choose the state machine 1, assign the program EP11 blink to the configuration. I'll set the timing frequency to 3000 Hz, just like the C version, and set the first LED in the blink group to be GPIO 0. Now that the PIO program is configured, I need to grab the PIO program starting address. As I mentioned earlier, I can get the starting address by reading the state machine instruction address register before the state machine is started. I'll use the SMAddress function we defined earlier to grab that value for the state machine 1. I'll print that information out later for giggles and grins. Now that I have the starting address, I can start state machine 1. Before we enter the main MicroPython program, let's determine the offset between the start of each loop from the top of the PIO program. We will use those values later when we set up our transfer statements. There is no good way to do this right now, just manually count. As you can see here, the start of loop 1 is 7 statements after the top of the PIO program. Loop 2 is 14 statements from the top, and loop 3 is 17 statements from the top. Now let's get into the main MicroPython program. The first loop, which blinks LED 0, is automatically initiated when the state machine starts, since it's at the top of the PIO program. The main program will let LED 0 blink for 10 seconds before it moves on to the next loop. The second part of the main program uses the jump workaround to transfer control to loop 1 of the PIO program. Here we force a set instruction to load the X register with the address of the start of loop 1. We get that by adding the start of the PIO program we obtained earlier to the loop offset we manually counted. Then force a move instruction to move the address from the X register to the program counter. This will transfer control to PIO loop 1, which will blink LED 1. After 10 seconds, the main program moves on to the third part, which will blink LED 2 by streaming instructions to the transmit FIFO. Here we set a counter to 0 and then use the jump workaround to transfer control to loop 2 of the PIO program. Now we'll enter a loop and execute it 14 times. Here we will use the PIO assembler to encode one instruction, set pins with 0 and no side set, and then put that value into the transmit FIFO. PIO loop 2 then pulls that value from the transmit FIFO into the output shift register, where it is then set to the control logic. This command turns off all the LEDs. Next, we will sleep for roughly a third of a second before we send a similar command to turn on LED by setting pins to 4. We'll sleep for another third of a second and then do it again 13 more times. In the fourth section of the main program, after we shift control to the fourth PIO loop using the jump workaround, we'll send the command to turn on LED 3. Since this command resides in the X register, I had to change the sequence from the C version. Originally, I sent the instruction to the X register before I transferred control to loop 3. However, the MicroPython jump workaround utilizes the X register, which wipes out any information that's stored there before the transfer is taken. That's the downside of using this workaround. You just have to be careful about using the X register during the transfer process. Then I enter a loop to load the transmit FIFO with 12 more instructions that blink LEDs 0 through 3 in sequence 3 times. I'll do that with 2 nested for loops. Then, just like the C version, when all the instructions have been loaded into the transmit FIFO, there are still 4 instructions in the FIFO that need to be processed by the PIO program before we can leave the loop. I'll sleep the main program for a little over 4 seconds to allow time for those instructions to be processed before moving on. Finally, I'll utilize the state machine restart function to transfer control back to loop 0. I could have also used the jump workaround, but I wanted to demonstrate restart instead. Let's start the program in Thani. I'll put up the equivalent C program output side by side for comparison. Note that the offset address for this PIO program is 6, meaning that the program starts 6 memory locations down from the top of memory. I believe that the PIO assembler loads programs up from the bottom of memory. As you can see, both versions track pretty closely during loops 0 and 1 when the PIO is in control of the timing. However, in loops 2 and 3, when the main C and MicroPython programs are controlling the timing, the MicroPython version gets just a little slower. Anyway, I think that this demonstrates that the force and exec instructions can work well with both platforms. Thanks for joining me today. We dug into forced and exec instructions in more detail. We first learned how we could make C-based PIO programs more portable by using public labels. Then we explored how MicroPython could perform forced and exec instructions. In the future, I'm considering reinventing the wheel by making a rudimentary VGA video generation program. The Raspberry Pi Foundation has created a very capable set of video display routines, but they're so full of features that they're difficult for me to follow. I'd like to make a very simple one so I can understand how it works, so stay tuned. If you like this video, or you think someone else might, please give it a thumbs up. If not, give it a thumbs down. The more likes this video has, the more YouTube will recommend it to others. Also, please leave a comment or suggestion for things to do. I hope to do more of these videos, so please subscribe and click on the bell for notifications of new videos. Let's get together next time for another day in Life with David. See you soon!